Hello, welcome back to Information Storage and Retrieval. So what we've been talking about lately is, oh, sorry, pouring my coffee. Um, what we've been discussing lately is how can we better rank our results, right? We've gone through all these steps to retrieve documents from our collection, pull them in and say, ooh, here's some things that I might want to give to the user. You know, they meet the minimum requirements of having these words present. But we've also just, we're diving into the ability to actually sort those ahead of time and not leave it up to the poor user to have to do that for us. So what we talked about last time involved a little bit of stuff like we can rank things based on findings from different regions, so different structured data, so fields and zones, right, that are possibly attached to many of our documents. At minimum, titles, right? That's almost always something on a given document. But also we got more into kind of looking at the word frequencies, the term frequencies, the inverse document frequencies of terms and all that. So we came up with a mathematical way of saying, is this term more or less related to this document, and then comparing across them to get our overlap. So, to recall, the goal is for any given query and the set of documents that we've retrieved in Boolean search, we want to really rearrange them all so that they are better represented in terms of their distance from the query in terms of the relevance of this document to the query. We want to be able to figure out that distance so that we can give our 10 blue links, right? Our top results so that the user can get on with evaluating their search on their own. So, we're trying to find numerical ways of comparing documents and queries so that we can get this ranking thing going. And we want to know the vibe is how close is the document to our query. And like I said, we have discussed a way to recast terms as this sort of numerical value with TF-IDF representation. Now, what I'm saying, I'm calling that a representation because this is saying essentially, well, this term has a numerical value with this data set. It has the term frequency for the current document, and it has an inverse document frequency across all the documents. So really what we're saying is we're losing track. We're kind of letting go of the term's actual word property, and we're now saying, okay, how does the math for this term work out? So to go over that again, the reminder from last time, how about the query some cars? What we're going to do when we're doing just basic TF-IDF overlap is we're going to say, I want to give priority to documents that mention those terms more often, so the term frequency, how often do those terms show up in that document, but then we're going to scale them based on their relevance within this entire system, right, in the collection, the inverse document frequency. We want to get this idea of how rare is this term in the collection. Rarer terms should probably get higher scores because they're more meaningful, right? If I'm searching the word the, well, if the collection is English, it's going to be a pointless addition, usually. Sometimes you need it for things like the who, right? So, some, as an example of that, some is not going to do that much work. It'll do some. It'll do a little bit of work. To help us find documents that are relevant, because only certain documents will probably use this particular phrasing. And then cars, well, if this is a database of cars that we're trying to build a search system for, well, that's not going to be very informative. But if it's across the whole internet, then cars is very informative. There's only so many subdomains of pages out there in the world that are going to use the concept of cars. So these things combined give us, some is contributing a little bit, but cars is contributing quite a lot. So their TF-IDF scores are going to be different, and we're going to then compare those to the documents. So we can enter a new direction using this same process, right? So under normal circumstances, we've always thought of, hey, our documents and our queries, they're terms. That we've chunked them into terms. We've built indexes based around those terms. We're thinking in terms of terms. We are using words, right? But this TF-IDF process, as I alluded to before, is a way that we can turn a term into a number. That's interesting because we're talking about distance now, right? Distance is a numerical value. The distance between two things, we might want some numbers involved. So, frequency of the term, TF, and then IDF is the scaling, right? We can do that for every term in a document and put it into a matrix. We can turn every document into a vector of these TF-IDF scores. Now, hang on. Isn't that just a term document incidence matrix? What are you trying to pull here? That's correct. Except we've elaborated it. So we remember the term document incidence matrix, right? We have a matrix, a full matrix. For every document, we have a little vector of the term incidence occurrences, right? Remember my I have a cat, right? So the vector of document 1 has 1111 and then a bunch of zeros. That is a numerical representation. Back then it was just these sort of Boolean values, right? It was a string of Boolean values we can then use to do our Boolean search. We talked about why this isn't actually the best format for Boolean search because it's large, it's inflexible. There's not much bang for your buck in terms of storing the actual relevant information, right? So we went with the inverted index, right? It's flexible, it's efficient storage, quick to access the text. Everything about the index is better for Boolean search. But we can evolve the term document incidence matrix. Because what we're getting into now is we're branching out into the more complex technique of, the harder problem. Now, while we spent a lot of time on Boolean search, the weirder problem, the harder problem is saying how far apart are these texts? So what we need is numbers to help that, or what we can use, I suppose. You don't need this. You could build a search system that's totally 100% happy just to do TF IDF overlap and like field and zone scores, right? Weighted scores for those fields and zones. But we can go this direction, so we're going to. So yeah, we can elaborate the incidence matrix and turn, instead of just the Boolean incidence value of, oh, was this term present or not, we can go the whole way and compute the TF-IDF score for the, across the collection, right? So in this case, we see that like the unique terms in my little fake toy version here, I and have, they only occur in this one document. They're going to have high scores. Whereas A occurs in a couple of documents and cat does too. They're a little bit lower. Is occurs in 3 documents. It's going to be very low, right? So this is an approach that, it's going to still suffer from the same issues that the term document incidence matrix did. It's going to be a lot of space, right? Every document's going to have a vector the same length as the entire dictionary of terms, right? But this is the only way to get to some more interesting stuff. So let's have a look. Let's look at a couple of documents here. Document 1, 1 banana, 2 banana, 3 banana, 4, right? Document 2, 1 fish, 2 fish, red fish, blue fish, okay? Document 3, roses are red, violets are blue. Okay, we can go through all the trouble to build ourselves the good old-fashioned incidence matrix, right? Document 1, document 2, document 3 are... Well, I'm just going to roll through it. I had them all animated. We don't need that. So we can tell where everything lives, right? This is the old approach, the incidence matrix approach. and we get our violets, right? But we would prefer the TF-IDF representation, right? Term frequency times inverse document frequency. So let's do all those. Do the same. Okay, so this is the term frequency, right? R happens twice in 3. Bananas 3 times in 1. Blue a couple times. Fish happens 4 times in that document. And so on, right? Lots of ones, lots of one-offs, right? Now, this is just how often does each one occur in that document. Remembering back that we can get this, we have to keep track of this stuff at the time that we build the index, but we can get it for free if we plan to use a positional index, right? So this information is available in the structures that we've discussed, but it's important to do it up front. So if we want to roll forward with these techniques, we need to do a little bit of planning. But the point is, these are not like inscrutable, right? Our term frequency is 2 in that document 3, and it's 0 in the others. Okay, now IDF, right? Remember that inverse document frequency is the log of the collection size over the number of documents with the term in it. Okay, let's do that for each one of these. Okay, so its document frequency is 1, right? It only occurs in document 3. Banana also is a one-off. Blue happens twice. Fish and 4 are one-offs, 1, and so on down the line. Again, give a sad shake to violets. Okay, so we have the document frequencies for each of these. And we have the collection size. We know that is 3, and then we can do the log thing. So we'll just jump forward. You would run this through. You do this math, do it programmatically, and bang, we end up with some different values, right? Banana's inverse document frequency is 0.48. It's a rare term, just like just like all the other ones that are one-offs, right? But then the other set we have is some of these appear in 2 documents. None of them appear in all 3. So we only have 2 actual values for inverse document frequency in this little toy collection. But we have it. So now we can compute this. So we're going to do the same thing again. We got the inverse document frequency for each one of these attached so that we can compute the rest. So R, that would be 2 term frequency times its inverse document frequency of 0.48, the score of 0.95. Banana, 0.48, so just as rare of a term as R in this collection, but it happens more often, so it has a higher score for the TF-IDF value. This is a rare term in our collection, and it happens a lot in that document. So that's going to have a really high, if we have something that matches this, if we have something that's calling for banana, that document's a good choice, right? Okay, continuing forward. Blue happens in 2 different documents, and it only happens once in each one, and it's a relatively frequent term in this collection, so it's going to have low scores, right? Continuing on, fish happens 4 times, and it only happens in 1 document, so it has an even stronger TF-IDF value than banana would. So anything that's going to search for fish, that's a very strong value. I know, of course, this is a very small toy document set, but the idea is that if there were, say, 100,000 values here, the documents that have these frequent values repeated multiple times have a very strong TF-IDF score for that particular term. So, continuing on, as usual, we can see the way they all come together, and we see sort of what are the highest terms. With I have it bolded the ones that are present at least, so all the zeros I've grayed out, and we see this is a way of looking at these documents in terms of their word frequencies and those words' rarities. This is powerful, as I said before, because now all of our documents, we've turned them into numerical vectors. Cool. Now what? So what? What do we do with this? Well, we can also do this with our queries. If I'm just searching for fish, my query ends up in the same zone, right? We can convert it to the same exact thing. This is just another document with just the word fish in it. This document's vector, it also only has fish once, right? It has 0.48 value, just like you would have for anything that was a relatively rare term that only happened one time. What if I search fish, 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 fish? Well, that's going to give a lot more emphasis to the documents that have heavier values. And what this gives us is our queries and our documents are now in the same numerical language. Doesn't matter how short a query is, it still has a numerical vector of TF-IDF scores that can fit the same, we can now run the same kinds of operations on our queries as we can on our documents. This is great. So, numerical representations. We can convert all of our term-based representations of our documents, right? The way that humans mostly see them and the way that our indexes have certainly seen them so far. And we can turn them into these numbers. And that's good because ranking is a distance calculation. It is a numerical process. So how do we do this? What kind of math can we do to figure out distances between vectors? Welcome to linear algebra. Don't worry, we're not, this is not, linear algebra is not a prerequisite for this course. And it is, it has some complexity to it, but we're going to just use the parts of it that we need to understand what's going on here. So we're going to do a little walk through some linear algebra. So here's your basic primer. Think back to normal algebra, right? You are trying to solve an equation for one particular value. What is what is y given x? And here's the equation. And you're trying to figure out, okay, what is the set of numbers that work here? What is the solution? How do I solve this? Linear algebra, as opposed to what you might think of as point-based algebra, is trying to solve for multiple values all at once. So instead of single values, we're working on vectors. So it really is just algebra, but kind of elaborated to do multiple things at once instead of just one thing at once. Okay, that's the conceptual basis for linear algebra. Now the question is, what's the fastest route to figure out what we're doing with this? Well, what's a vector, right? We talk about vectors as these sort of like a set of values, right? An array of values, right? A vector is just that, and it's just like a list or an array. It's just a set of numbers that we have set aside, a vector. What we can do, the way you can visualize a vector in your mind, though, is every value in that vector is one of the vector's dimensions, right? So you can look at a graph, a line on a graph. So this vector goes from 0, 0 to its vector value is 2, 3, right? So it's at position x equals 2, position y equals 3. So 2, 3 is a vector with 2 dimensions. It has 2 values. And again, the kind of the point of thinking of them this way is so that it's a little bit easier to visualize them, right? So these are, this vector present on the screen right now is one vector with 2 values. Scale that up once. We can also do vectors with 3 values, right? And now look at this. This is just the same as we saw before. It's x, y, and now there's a z-axis. And okay, we can do thetas and values and all this stuff, but it's just another line, right? You see it, it's a line kind of pointing up towards us into space. It has a particular x value, that little bottom left bar. It has a particular y value, a little bit smaller than the x, and it has a particular z value, which is a little bit bigger than both of those. And that represents its point in space, right? So vectors can have any number of dimensions. I mean, 3D is just 3 dimensions, 3 values in the vector. Now, the problem is, if we want to keep going, representing 4-dimensional vectors, that gets a little harder, because, we are limited. We are 3-dimensional entities. We see space in 3 dimensions. So we get a little bit beyond our ability to simply represent all of this, but the point is that this all still holds. So that if we want to scale all the way up to, say, document vectors, the things that we've been creating, these are just high-dimensional vectors. They have t dimensions, where t is the number of terms in our entire dictionary. That's a lot of dimensions when we're trying to think about a 3D shape, but again, it's just a set of numbers, right? So this is hard to represent. And while we're working through the examples, we'll stick to the low-dimensional stuff, the visualizations of those. But it all works, no matter how large they get. So, looking back at our documents we've been playing with, let's look at just 1 and red. Okay. 1 is one of the dimensions. Red is one of the other dimensions, right? We have chosen just these 2 values to think about our documents in terms of them, right? So, if we wanted to look at just this one little 2-dimensional chunk of the documents, 1 and red, right? So, document 1, what kind of value are we expecting here? Ignoring sort of the exact numbers of these axes, let's look at, okay, so document 1 has 1 represented, and its TF-IDF value is small, 0.18. Its value for red is non-existent. So the document vector between these 2 particular terms for document 1 is right there on the first axis. It has no representation of red, but it has some representation of 1. Document 2, well, that has both of them, right? It has a representation of the word 1, and it has a representation of the word red in equal measure. So it's going to have a vector for these 2 values that points up there, right? And then document 3, you can see already it's kind of the same deal as document 1, it's just the opposite direction. It only represents red, and 1 is not there at all. So this gives us sort of, we're charting the space just by narrowing in on a couple of the dimensions available in these vectors. And we're seeing, interesting, these are different, sort of visually different, right? Document 1 exists in a different little space, it's part of the space, than documents 2 and 3 do. So, how can we move forward with this? What can we do? How can we compare the values of these vectors? Remember, that's the goal. We're trying to get a distance score between 2 vectors, 2 document vectors, and we want to see, we want to see which one's is closest. How can we compare 2 vectors? Thankfully, that answer is very clear. Essentially, you're trying to get the angle between them. We've all done a little bit of geometry, a little trig, somewhere in our pipelines. This is actually very easy to compute. So the cosine of the angle between the vectors in question ends up being, okay, for specificity's sake, dot product over the magnitude of both vectors. So the distance, and then as compared to the magnitudes, it's sort of like a normalized distance. It doesn't matter so much. The way you can think of cosine similarity, which is the actual thing we will compute, is what's the angle? So, computing cosine similarity, just a note on if we go to implement this, it's anywhere, right? Any set of math functions has this available. Computers are good at this kind of stuff. So we're not going to dive deep into how dot products work and how magnitudes factor in and all that stuff. But this is how a computer would solve it. And just know that it's available, but also that it's kind of expensive. You're going to have to run. This is a linear process, as we can expect, linear algebra. It's going to have to run across the entire length of the vector, right? But it's powerful because by computing the angle between two of these vectors, we get a nearness score. We get an idea of, okay, how far apart are these two things? So, this is pretty neat. We found a way to take two vectors that represent documents or queries, right? And we can compare them directly. We say, hey, based on the makeup, the componential makeup of your terms that exist inside you, document and query, I can turn all those into numbers and compute a value that tells me how far apart they are. And from there, you just rank based on the cosine similarity between the query and each document. So, let's do an example of all of that. Okay. Again, we're going to stick to just 3 dimensions, but remember that trust. Trust that this stuff, it works the same even if you add 4, 5, 6, or 500 dimensions. It's just a mathematical process of running through them all and saying, hey, what's the angle? I know it's hard to picture an angle in 4-dimensional or 5-dimensional space, but that's still more or less what it's doing. How close are these two things while taking into account all of the axes that are available? So, let's look at the dimensions of cat, so one of the terms available in our collection, dog, one of the terms available in our collection, and capybara, right? So, document 1 kind of talks about all of them in equal measure. Maybe it's like sort of a dictionary of small mammals, right? Document 1, it's dealing with all of them. So to remind, to make clear, document 1 has a value for capybara as kind of the parallel line to capybara. It has a value for dog, the parallel line to dog, and it has a value for cat. Maybe he talked about cats a little more. Who knows? Maybe they're more present in the introduction, right? We also have document 2. Document 2 talks about cats and dogs quite a lot. And it doesn't talk about capybaras at all. The value for capybara is 0, and the values for dogs and cats are higher. So maybe this one was more of a pet guide or something, right? Not a lot of people have capybaras for pets, so it's a guide of those things. And then finally, our third document talks about cats a little bit, but it's mostly about capybaras. This is Capybaras Monthly, the magazine dedicated to capybaras. Everything capybaras. Oh my God, capybaras. And maybe they compare them to cats or something, right? So the idea, though, is that that vector for capybara is real strong on the capybara axis and has a very minor connection to cats on the cat axis. So, but right off the bat, you can see visually how very different these documents are in vector space, in this, the space of these vectors in this numerical way. We have captured the numbers that represent how much each of these documents talk about and sort of pertain to each of these terms. We've charted them in a numerical space. So now we can do our cosine similarity questions and compute the distances between these documents and our queries. What if we get this query? Query 1. cats, but also capybaras. Now remember, we're only looking at the values in these vectors, or in this vector space, for cats and capybaras and dogs. And the but also is kind of, those are probably not very high. Those are probably kind of frequent terms anyway. They're not going to factor in that much to these future calculations. So cats, but also capybaras. Well, this talks about each of them in equal measure. If we look at the capybara plane, it'll just be represented there on those two. And dog, it's not going to be represented at all. There's no dog in this query at all, right? So now we would say, well, this one, and so remember, we're thinking about the angles between them. The angle between this one and doc 2 is almost irrelevant because that's not even really going to show up in the search, right? So we're really focused on documents 1 and document 3. So the question is, which document is it closer to? Well, in this case, you can tell it's a little far off from document 3. And document 1, even though it's a little hard to tell because it's kind of pointing up toward us in space. You can see, its little shadow down there at the point between all the lines. But it seems pretty clear that the query 1 is going to rest closest to document 1 because document 1 is representing all these things in equal measure, right? But what if we got this query? Query 2. Cats, but more importantly, capybaras, 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 I'm crazy for capybaras. Well, that's going to ramp that particular query up to the point of it's no longer really connected to document 1, is it? We'll probably want to give this person capybaras monthly. And so we will. So that gets us into the idea of the vector space model. It is, again, everything that we've done so far, I hope it's clear that the individual steps are quite simple. We know how to get the term frequency out of a document for a term. We know how to get the document frequency and turn it into an inverse document frequency. And then we would ostensibly be quite easy to just build the matrix, right? We turn all of our documents and queries into these vectors. And then, the vectors have the TF-IDF value in them. And then we use linear algebra. A simple cosine similarity is the kind of thing that you could call once. You just say, hey, here's a vector and here's another vector. Give me the cosine similarity between those two. And again, the math, the system that you're using would be able to do that. You wouldn't trouble yourself with it. So again, computing the angle between these things, the distance between these things, is relevant. It is straightforward when you think of it just as, okay, I've gotten these things into vectors. Now I want to know how far apart they are. That's typically going to be one function call to give you the result. So what you would then do is go through each document after we've kind of chunked the query and all the documents into these vector spaces. We can now say, hey, well, what's the similarity score for each one? I'm going to percolate the one with the closest value to the top. That top value should be closest to your thing. So, some considerations, right? We want to talk about the possibilities here and the things to be careful of when you're going to do this. So, computing cosine similarity is expensive. Like I said, you have to run through all the dimensions of all of the document vectors that you're working with. And it kind of feels like a step backwards, right? Oh, well, now we're just doing the incidence matrix all over again. Why wouldn't we just do all of our search using the vector space? You kind of could, but we can hold on to all of these vectorized forms somewhere else, right? As we talked about before, you can store the big stuff off-site. You can not literally off-site, but like put it on the hard disk. Don't keep it in memory. Don't clog everything up. You don't need to hang on to these vectors. You can just go get them when they're needed, right? So if Boolean search turns up a document, hey, go grab the vectors for me. While you are pulling up the documents, get the vectors too. So It's just really cool. I think this is the neatest step in the process. It's probably the most complex. It involves the most steps from start to finish, the most numerical processing, the most math kind of stuff going on. But I think it's really neat because it gives us this whole new way to think about our documents and queries. So, yeah, the vector space model is powerful. Again, it has some costs, but I think it's worth implementing because it just kind of allows a new perspective on these different unstructured piles of data. And technically, you could get into a technique. I discussed it here because I've looked into it from that supplemental text. We might come back to it, but you can kind of skip Boolean search if you and all of indexing if you just want to go and find the numerically closest document. Now you might think, oh, wait, what? I'm going to now iterate over every single document in the entire structure? That seems crazy, and that is crazy. That's why there are a lot of other kind of nuanced and advanced things you would do to prepare your collection for that. Again, we won't get into that right now, but that's just to point out that this method, this model of thinking about our documents, it allows you to do things in a unique way and kind of forego some of the other stuff we've talked about. Moreover, it allows for some interesting things that you might be used to from current technology on this stuff, right? Similar content searches, right? You could take the current document that the user is reading, and you could just use it as a query and just, hey, go find other documents that are close to this one in terms of their vectorized forms. The same way we might have used this to skip Boolean search in the first place, you can then chain them. You can search from this one to the next one, from that one to another one, right? A lot of recommendation engines use things like this. So, and you can even do, okay, so this query came up and you found what you were looking for maybe, but here's a similar query that maybe had other results, right? The possibilities are endless. Once you know how to do one of these tools, you can come up with new fancy ways to implement it. Okay, so that's vector space. That's how we can think about our documents numerically. And more importantly, this leads us to a complete system. We've been kind of all over the place. We've touched on a lot of topics and concepts that cover different areas of these systems, but at this point, our understanding of an information retrieval system is kind of complete. Now, that doesn't mean that there's not other ways to do many of these things and ways to combine them and things that we sort of left on the cutting room floor a little bit, but at the core, the way that all the information flows into the system and out as results, we've covered it. So we take unstructured data through the normalization, tokenizing, and indexing processes, and now vectorizing, so that we can do some fun vector stuff later. And we take the nebulous information need from the user, we correct it, we found ways to correct it, we can expand it into sort of a more complete query, and a correct one, so a good query. And then we do our Boolean search to go and retrieve some relevant documents, and finally we rank them, give them scores, to measure how relevant those documents are to the query, and then present them as the results. We have taken our information need and unstructured results, run them through our system, unstructured data, run through our system, and gotten search results. We have created a Google. This is how it works. So, to look at our evolving system map, this is all the things we've kind of touched on. And again, we've talked about some things that aren't here. There was just some space issues. So I'll do a little bit more complete version of all this soon. So we have added the idea that, well, we're also going to sometimes need to make some big old document vectors so that we can reference them later. So we have some vectorization happening on the sort of data side. And then finally, so we can take that and various other things from our search, our Boolean search, and we can start our ranking process. We got zone scores, we've got TF-IDF overlap, and we've got the cosine similarity for the vectors. That gets us a results page. This is it. We've done it. Ta-da! Okay, so what does that mean for the rest of the course? Well, from here, we're going to touch on some other topics kind of surrounding all these core mechanisms, some things that we haven't really discussed before, maybe some broader things about how the actual fuller internet works, some, I don't know, some human interest stories I have queued up for you. So there's some, you know, we are beyond now, we have just crossed the finish line of all like the sort of the core mechanical things that I want you to really get in full. And we're going to focus more on some conceptual things from here on, but also we're going to have a little bit more frequent assignments to kind of detail how these things work in code, how to build these things, right? So I want you to have that working understanding of everything so far, and actually not everything so far, but many of the things we talked about we will implement. And I'll also occasionally have some review of just how pieces fit together, right? We've covered so much, and even if I just go back a slide real quick, there's a lot here. And remembering how this all flows, which parts connect to each other, it's worth doing some review. So don't worry if it's still kind of overwhelming. I promise you've come this far. You've learned about each one of these things to an extent. Maybe not text extraction and collecting so much, but again, these are things that we can touch on. But the idea is we're gonna keep elaborating on your ability to put all this stuff together, and we're going to kind of use this now to talk about other interesting ideas out there in the world. Okay, that's it for today. As usual, a final thought. What are other ways the unstructured information in your life, especially online, can or often is converted into more numerical forms? All right, thanks. Take care.